Welcome back to the video series entitled From the Ancient Greeks to Isaac Newton, Early Astronomers and the Birth of Science. Lecture 3, Brahe and Kepler. As you can see from our timeline, the lives of Tycho Brahe and Johannes Kepler overlapped to a considerable degree. In fact, they worked together as colleagues for a brief period of time. Now, it has become customary to refer to Tycho Brahe simply as Tycho, possibly because it's easier for English speakers to say. In any case, we begin with Tycho. Tycho had a true passion for gazing at the night sky. He was using instruments known as sextants and quadrants. They allowed him to measure the ever-changing angles between planets and the fixed stars. Tycho was meticulous in recording detailed observations. This is from one of his notebooks. He is observing the great comet of 1577 and carefully recording its position night after night. He was continually improving his instruments to provide greater and greater accuracy. One of his quadrants filled up the greater part of a large room. In 1572, Tycho observed the sudden appearance in the night sky of a new star. In fact, what he saw was what we now call a supernova. He published his findings in a small book entitled De Nova Stella, meaning On a New Star. The illustration on the right is a page from his book showing the new star, circled in red, in relation to known stars of the constellation Cassiopeia. His discovery was controversial because it disproved the belief, widely accepted since the time of the ancient Greeks, that the realm of the stars was eternally unchanging. The discovery, along with his other published works, made him perhaps the most renowned astronomer in all of Europe. For most of his career, he was supported financially by King Frederick II of Denmark. As part of that arrangement, Tycho served as royal astrologer. The job entailed compiling an annual almanac that predicted the fortunes of the kingdom for the year, based on the influence of the stars. As a matter of fact, throughout the Middle Ages and Renaissance, astrology was typically taught at universities as part of the astronomy curriculum. For many astronomers, the practice of astrology helped pay the bills. When King Frederick died, Tycho increasingly fell out of favor with the new court, and as a result of dwindling financial support, Tycho's career prospects took a turn for the worse. Luckily, Tycho found a new patron in Rudolf II, the Holy Roman Emperor. Rudolf had just moved the imperial capital from Vienna to Prague, with the clear ambition to make Prague one of the top cultural centers of the late Renaissance. Rudolf wanted to make Prague not only a center for the arts, but also a center of learning. Rudolf was especially interested in astronomy and astrology, and he was eager to make Tycho the official imperial astronomer. Tycho gladly accepted the position. He would soon be joined in Prague by another rising star in the field of astronomy, and their brief partnership would be instrumental in advancing the scientific revolution toward its climax. Kepler was a mathematical whiz-kid who developed a passion for astronomy at a young age. He studied mathematics and astronomy at the University of Tübingen, where he became a staunch supporter of the Copernican system for both theoretical and theological reasons. Upon graduation, he took a job as a mathematics teacher, but found time to write about his theories on the structure of the solar system. He published a book entitled Mysterium Cosmographicum, which gained him a favorable reputation among European astronomers. He attracted the attention of Tycho Brahe, and they began a correspondence discussing and debating their ideas. Tycho was impressed enough to invite Kepler to work with him in Prague. At that time, Kepler was convinced that God's plan for the universe would be based on the abstract perfection of geometric objects. In his early approach to astronomy, his guiding principles constituted a sort of geometrical mysticism. The Mysterium Cosmographicum focused on the relative sizes of the planetary orbits. For Kepler, as for Copernicus, each orbit defined a circle of a particular radius, and he had a pretty good idea of the ratio between the radii of any two adjacent circles. We talked about this in the last video, how our friend, the right triangle, allowed for the calculation of orbital radii relative to that of the Earth. Let's imagine what Kepler might have done. He starts making a table. There are 6 known planets and 5 pairs of adjacent orbits. Kepler was interested in the ratio of orbital radii within each pair. Note that ratios I have listed here are based on our current knowledge of average distances from the Sun. The ratios that he was using were no doubt somewhat different. In any case, he found that the ratios varied over a wide range with no clear pattern. This irregularity puzzles him. It bothers him. He wants an explanation for it, some sort of geometrical underpinning. So he sees what he can do with regular polygons. Kepler starts with a square. He draws an inscribed circle. He draws a circumscribed circle. He poses a question. What is the ratio of the larger to the shorter radius when considering these two circles? The answer he found was 1.41. He tried the same thing with an equilateral triangle. In that case, he found the ratio to be 1.56. He goes back to his table and he puts in a column for regular polygons and one for the ratios of their circumscribed to inscribed circles. He found an appropriate place in his table for the ratios of the square and the equilateral triangle so that they closely matched the ratios for Earth to Venus and Mars to Earth, respectively. Things looked promising at first, but when he failed to find good matches using other regular polygons, he realized that this plan was a dead end. So he decided to think in terms of 3 dimensions, which brought him to the 5 Platonic solids. A Platonic solid is a 3-dimensional object with flat surfaces, such that all surfaces are identical regular polygons. Why are there only 5? There is something mysterious about them. Or perhaps, Kepler thought, they are the solution to a grand cosmic mystery. So now he thinks of each orbital radius as defining a sphere. There are 6 planets and 5 gaps between their orbital spheres. He puts a Platonic solid into each gap, starting from closest to the Sun and moving outward. He put in an octahedron, an icosahedron, a dodecahedron, a tetrahedron, and finally a cube. Let me show you 3 examples just to give you the idea. Here's an octahedron between the orbital spheres of Mercury and Venus. Here we see an icosahedron sandwiched between the spheres of Venus and Earth. And here's a tetrahedron snuggled in between the orbital spheres of Mars and Jupiter. So now he creates a modified table. The left-hand column is for the Platonic solids, and the second column is for the ratio of radii of circumscribed to inscribed spheres. And when he fills in that second column with the known ratios for the Platonic solids, he is very pleased with the fit. He understands that there is still a level of uncertainty for the true ratios of planetary orbital radii pairs, and so he's not upset by the small discrepancies. Here's an illustration from Mysterium Cosmographicum. Of course, it was all wrong, and Kepler would later openly admit that. The importance of the book, however, was that it attracted the attention of Tycho Brahe. Now, the relationship between Tycho and Kepler was turbulent at times, complicated by a combination of mutual respect and mutual resentment. They were very different people. Tycho was born to nobility. Kepler was raised in relative poverty. Tycho was arrogant and self-aggrandizing, while Kepler was modest and self-effacing. Tycho was the fanatical empiricist, the meticulous collector of data. Kepler was the idealistic theorist, searching for the grand design that underlay the structure of the universe. But like any good theorist, Kepler knew that his theories were worthless unless there was data to back them up. Kepler knew that Tycho had a treasure trove of data, so he was delighted when handed the task of trying to make sense of Tycho's data on the orbit of Mars. This assignment was serendipitous in the sense that, because the orbit of Mars is the most eccentric among those of all the planets, it would force Kepler to abandon his cherished but incorrect idea that planetary orbits were necessarily circular. The data pointed him to an undeniable and monumental truth. The orbit of Mars was not a circle. Meanwhile, when Tycho died, Kepler naturally expected to take possession of all of Tycho's data. However, Tycho's heirs had other ideas. They viewed those records as valuable assets belonging to Tycho's estate and tried to establish sole right to them. Fortunately for the progress of science, Kepler eventually won that battle, although possibly by illegitimate means. To his credit, Kepler put aside his Platonic solids theory and went looking for an answer that fit the data. At one point, he considered an ovoid or egg-shaped orbit. I guess the sun would be the yoke. That's an astronomy joke. But the joke, or the yoke, was on Kepler. When he finally realized that the answer was an ellipse, he was surprised that no one had thought of it earlier. He inferred that all planetary orbits are elliptical with the sun at one focus. This became Kepler's first law. You may recall some of the principal features of ellipses from geometry class. Anyway, Kepler's first law is that planets move in elliptical orbits with the sun at one focus. Kepler also knew that a planet's orbital speed was fastest when it was closest to the sun and slowest when it was farthest away. After some trial and error, he came up with his second law. Planets sweep out equal areas in equal times. In this diagram, A1 and A2 represent the areas swept out by a planet at different points in its orbit over a 1-month period of time in each case. A1 equals A2 because Kepler found that the higher speed of the planet, when on the left-hand side of this illustration, exactly compensates for the shorter distance from the sun, when all is compared to the planet when on the right-hand side of this illustration. The period of a planet's orbit is simply the time it takes for the planet to make one full trip around the sun. The period of an orbit is commonly represented by a capital T. Kepler's third law simply states that the square of the period is proportional to the cube of the semi-major axis, which is commonly represented with a small a. Kepler's three laws are all correct. He arrived at them by a process of trial and error. They describe patterns within the data, but he never found an underlying set of fundamental laws that would account for those patterns. That undertaking became known as solving the Kepler problem, and that's where Newton is going to come in. Before we get to Newton, it's important to point out that Kepler had developed some idea about gravity, although in his works, which were written in Latin, he did not use the Latin cognate gravitas. Here's what he actually wrote. There is an attractive power or a mutual corporeal disposition among kindred bodies to unite or join together. If two stones were set near one another in some place in the world outside the sphere of influence of a third kindred body, these stones would come together in an intermediate place, each approaching the other by a space proportional to the mass of the other. This statement that there is an attractive power proportional to the masses of the two bodies was a highly astute proposal and provided the correct starting point for anyone aiming to solve the Kepler problem. Kepler made one other proposal that missed the mark, but not by much. Kepler believed that what we now call gravity decreased in strength in proportion to the reciprocal of the distance between the bodies, i.e., strength is proportional to 1 divided by d, the distance. Several scholars later began to suspect, correctly, but for reasons that perhaps varied or were not entirely clear, that the strength of gravity was inversely proportional to the square of the distance separating the two bodies. It fell to Newton to prove this relationship, known as the inverse square law. Before we move on, I want to leave you with one last comment in praise of one of Kepler's virtues as a scientist. Professor James Madden of the Department of Mathematics at Louisiana State University wrote that Kepler was one of the most open and unabashed of mathematical writers. He never hesitated to describe blunders, wrong turns, and dead ends alongside his true discoveries. You are now prepared to proceed to Lecture 4, Isaac Newton.